job recording. So hopefully it's actually recording now and it'll sync better with the lecture slides. Okay. So what we're going to talk about today is go through Chapter 1. We kind of already reviewed some of that material in the introduction, talking about how old chemistry is and how cool it is. And then we'll move into Chapter 3 based on the 7th edition. If you're using the 6th edition, it's Chapter 4, I think. So let's go ahead and get started with this. Homework. So I went through and took a look at these two chapters. And you'll notice that I've got a bunch of words here, but typically homework problems are assigned based on number. There's a reason there aren't any numbers. So I started to go through and pick problems and was like, this is a definition question. So making you write it down, while that does help you remember, and there are some people that helps, other people it just ends up being busy work. Okay? So I'm not going to look for homework questions being answered on the day of the exam. So when you turn in your homework booklet, I won't look specifically for questions from Chapter 1 or Chapter 3. Okay? That said, there are problems in there that you should be working. Okay? They are ultimately just memorization questions. And again, it's just a single answer. There's no work to be shown. So again, assigning that problem is just kind of a waste. Okay? For instance, if we go into homework 3, element names and symbols. Some of the questions are, what is the element name for H? Hydrogen. Okay, you knew the answer. Why should you write it down? Okay, so that's why there aren't any questions specifically labeled next to these. What I did go through and do is highlight the section titles to kind of address the types of questions that you could see within each of these. So what I would recommend you do is when you try and go through and look for homework within the textbook, read through it, get a feel for what's going on, and then just work some of those problems. Okay? If they're asking you to know what element names are, start scanning through the periodic table and figuring out what those element names are. Start getting comfortable with referencing that information. Okay? Again, there's not a lot I can do to really check homework except just make you do busy work. And I think that's a bit of a waste. Okay? Does that make sense? Okay. One other thing I want to address with that, when it comes to the homework is due the day of the exam. I've had a lot of people telling me, oh, I'm going to turn in the homework next week. There's no homework to turn in every week. You turn it in the day of the exam. Okay? Only the day of the exam. Is there anything else in there? No. Okay, I think the rest of that description. You'll notice also this slide is different if you downloaded the slides than what was posted. That's because there was a little bit of confusion this morning, so I tried to clarify it with this slide. Okay? So if we go back to Chapter 1, I didn't think this example was going to work very well, but I was actually surprised. This morning worked out really well. Okay, so we can think about why science. So if we came in, or you all came in here, and I had, let's say, 20 strawberry pies at the front of the classroom, just sitting there. Okay? There's a few different approaches on how you could come in and look at that. If you were a pessimist, you probably came in and he said, that guy's just going to sit and eat pie in front of me all day. And that's just rude because I really like strawberry pie. Okay? The optimist might come, oh, he's a nice guy, he's going to share with everybody. I do share. I probably won't be strawberry pies. But we do have that possibility. The scientist comes in, sits down, and says, I can make a better pie than that. Okay? So that's what science is about, is taking a look at some observation and trying to figure out how it was built, why it was built, and then try and do it better. Okay? That's almost everything that we're doing with science. Okay? So let's take an approach. Let's see what we can do with this. If you were going to go through and came in as a scientist, you say, I'm going to make a better pie. Okay? What might be the first step to do? What things make up this pie? Well, you all had pie, right? Okay. What things made up this pie? You could go as far as ingredients, but I wanted to go even... Whoops, don't do that. Okay. I heard a good answer in there. A crust. Okay, we need some strawberries. Sugar. I'm going to change your sugar into some kind of glaze. Okay. So we could go out and say, okay, now we know those basic pieces. I can go to the store, and I can buy some strawberries. I can buy a crust, and I can buy a glaze, and I can just smash them all together, and I got a strawberry pie. It doesn't quite work that way. So what's an extra thing that we might need beyond just a crust, strawberries, and a glaze? Yes, and we'll get into the recipe in a little bit. Okay, we could look for an oven, which is actually something that wasn't suggested at this point, but that works. An oven. But if I just take strawberries, crust, and glaze and smash them all together and throw them in the oven, what am I going to end up with? A big old molten mass of nastiness in my oven. So we need something to hold it all. So we also need that pie tin.
Aren't you going to need some pectin?
We're about to get there. Okay. So we could collect all of these things together, put it together, and yes, we now have this pie. Okay? Except I like to cook. And I like to think of myself as a good cook. And I'm going to tell you right now, if that's all you got together, my pie beats you. Okay? You got to make a better pie. So how could you improve your recipe or your pie? Okay, so you could start to add in other things. Is there a way that we could make the crust better than just purchasing it from the store? We can start to make the crust. Well, how do you make the crust? What do you need to put together for a crust? Everybody says eggs. Does eggs really go on a pie crust? Okay, I'm seeing a lot of people say that, but it's not a big deal. That's just new to me. Okay, so let's throw up egg. It's a possible ingredient. What else could we throw? Flour. Water. Baking soda was actually kind of new to me too.
Some good old lard in there.
There we go. That was, yeah. So actually that brings up an interesting point, because this morning they said butter. But we could also go with lard.
Good old Crisco.
Okay. There's other things we could throw in there. We could get sugar in there if we wanted to make the crust sweet. Maybe some cinnamon, spice it up a little bit. Chili flakes, just to make sure it's got that extra zing. My pies are crazy.
That sounds like it, man. You're on the hook now.
And so we could then start to build this. Okay, but if we look closer at this, and it's good that we got the lard suggestion here, butter versus lard. Okay, well, which one makes a better crust?
Lard makes it flakier.
So now we're going to start to look at different preferences. So we have to generate a threshold, and there's a threshold that goes towards building this pie crust. And that threshold is dependent on everybody's personal opinions. That's why eggs are still up there. You could use an egg. Okay? But then between butter versus lard, okay, which one's better? You say lard makes a better crust, or a flakier crust, but I might argue that butter tastes a heck of a lot better than just straight lard. Okay? So there's varying amounts to how you put this together. Okay? We could also look at the qualities. Is there only one type of butter? Salted butter. There's unsalted butter. Can you taste the difference between those? Yeah. So which one do you use? Right? Do you buy the one that comes into the store, or do you go to the cow and, I guess you don't milk butter out of the cow, but it's close enough. Get the butter straight from the cow. Could we taste a difference then? Some people could, and the biggest question there is potentially. So we have to decide where our threshold is when we go through to evaluate this. So a lot of science comes back to what's that limit? Okay? What's going to be good enough that it's going to cover exactly all I need to? Anything beyond that is pointless. Okay? You could take this back to buying pretty much anything out there. You can buy a really expensive car that has all sorts of fancy suspension systems in it. That's pretty awesome. Are you going to know that that suspension system is there? Probably 90% of the people don't even know it's there. But that makes that car so much more expensive. Whereas if you get rid of the suspension system, you now have a cheaper car that does the exact same thing. Okay? So there's always a threshold to what we're trying to deal with. And science is all about finding that threshold and then maximizing to hit that point, okay, as best we can. Okay? So that's one of our goals. So a lot of the things that we went through here is first off breaking it down into the pieces and then deciding, okay, well, what's the threshold that we're trying to beat? In our very first case, the store-bought crust and the store-bought, you're always going to buy strawberries from the store, but no, I guess you could make them. You can grow your own strawberries. Okay? You've got those options to put it all together. but your threshold is comparing it to something else. You're going to make it better or change it to account for that. So we always try and break things down into the smallest parts that are going to allow us to build the best that we possibly can within that tolerance level. Okay? That's one of the things that makes science fun, is we're really just trying to figure out how everything was put together and build from that. Okay? I'm sure I talked about pies more than that in the morning, but I don't remember what else I said, so let's just run with it. Okay, so let's go back to the scientific method on how we're going to approach this. Your textbook has a very similar diagram to this, but they branch up. Science, for some reason, always seems to branch downwards, at least, I guess philosophically speaking, it tends to branch downwards. So science is all about learning something new. Okay? It doesn't matter what that something is, but it's about learning anything new. How does it work? Why does it work? Can we make it better? Okay? So that's our ultimate goal. So the first thing we'll do is come up with some observation. So we came in, saw there was a strawberry pie. Now I'm going to make it better. Just to be like, neener, 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 I can make it better than you. Okay? So we then have to come up with some kind of hypothesis. Yes, I can make this better. Okay? Once you've got that overarching idea on what you're going to end up doing, then what do you have to do? You have to actually execute it. Okay? You have to build the experiment to see if that hypothesis is indeed valid. Okay? How many of you have cooked pies before? Okay. All of you that cook pies, you're not allowed to participate anymore. I've cooked a lot of pies. I'm a really good pie chef, baker, one of those. Okay? So anybody that's cooked pie can't compete with me. What are the odds that everybody else, when they go through and cook their pie, is going to be as good as mine? Not really good. Which means, and this is the biggest part of science that almost always gets left out, what's the end result of this experiment? Failure. Okay? 90% of science, 95% of science is failure. Okay? And this is one of the reasons why students get frustrated with science, because you spend 95% of the time failing. And it's a crushing emotion. We just feel terrible for it. Okay? And that's why a lot of people, when they go through and teach, they tend to avoid the word failure. Okay? I disagree. Let's be honest with it. Let's come out straight ahead and say it. Okay? We are all about failure in science. Where science actually becomes cool and interesting is that we don't stop at that failure. Okay? We don't stop at the end of our experiment failing, and we double back to our hypothesis and say, okay, we need to change how we approached this problem. We missed something. Maybe it is really important that we use just lard. Okay, so now we redo it. We come through and retest our experiment with that new assumption, and what happens? I said 95% of the time your experiment ends in failure, so what just happened? No, still, that was only the second time. You fail again. So you go back to your hypothesis, change the hypothesis. Okay, something else has to happen here. What do I adjust? How do I fix and move forward? Then we do it again. What happens? Hey, good, we got the numbers now. Failure again. Okay? And we keep doing it and keep doing it and keep doing it until eventually you can come back and say, my pie is better than your pie. Neener, neener, neener. Okay? And that's what science is really about, shoving it in someone else's face. Okay? So after we've failed enough times and we keep pushing and we keep working at it, we can eventually then move beyond the experiment and start to move into two different other categories. We can end up with natural laws where we have direct observable measurements. Okay? So that we can actually measure these results. When it comes to a pie, okay, do you think we're going to be able to build a natural law about the quality of a pie? Why not?
There's so many different standards. You could be like, you could base it off of taste or like.
Exactly right. We could look at different standards. Okay? And if we said, even with taste, okay, is everybody's taste the exact same? No, clearly not. Look at me versus you guys. I'm definitely dressed better, right? Okay. So taste is a very subjective thing. So we can't push into a natural law. but we could start to come up with scientific theories. These theories can be further investigated and expounded upon, and we can propagate those into even more experiments and even new hypotheses. Okay? So science is driven by failure, and it's that repetitive action of pounding your head against the wall, okay, waiting for that 5% chance. Okay, by the way, it got more difficult as the day went. The morning was 10% chance. 5% chance you get it right. Okay? And there's a lot of scientists that if you ask them, why did you stick with science? The reason they stuck with it is because that one time they did one experiment and it worked. They said, holy crap, I'm a genius. And they feel ecstatic. And then they go back into the lab and fail again. Okay? And they go, well, I got to go find that again. It's almost like science is an addiction. Okay? You get addicted to that high of getting it right and figuring that problem out. Okay? The unfortunate part is that you have to deal with the other 90% of just crappy feeling the rest of the time. Okay? Okay? Or you turn around and just turn it into a better situation. It's not so much failure. It's that I learned that that thing didn't work. Okay? How do I adjust? Okay? If we go back to my research, my advisor said, just play with this experiment real quickly. Let's just see how it works. It won't take more than a week. It took 5 years. Okay? What happened? Variables. Okay? It turned out that when we played with it once, we're like, okay, that's an interesting result, so we tried to do it again. Totally different results. Okay, that's not good. We've got to control something. Okay, what was wrong? Well, it rained the day I did it the first time. It didn't rain the second time. So I just waited until it rained. Which took 5 years, but eventually it rains again in Arizona, and I test the experiment again, and it worked. No, it was actually the reverse. Okay, so there's all sorts of other variables that we would have to take into consideration. The presence of oxygen. Okay, is it under vacuum? Is there water in the atmosphere? There's all these crazy variables that can add up and really change the overall results. And that's what science is about, is finding those variables and narrowing it down. Finding out which ones are going to adjust the threshold, which ones don't affect the threshold. Okay? So while that may sound kind of depressing to some of you, hopefully that sounds exciting to some of you. Okay? The idea is that we are going to continue to learn and build from the mistakes that were made in the past, and that's what the class is about, is looking at everybody's successes. Okay? So, chemistry's role and kind of the overarching idea behind all sciences. Okay? We've got mathematics and physics, which end up getting super theoretical. Okay? You're looking at just raw numbers, and somehow or another these raw numbers mean a bond forms or a bond breaks. Okay? The rock falls or the rock rises. I don't know why a rock would rise. Someone lifted it. There we go. There's an explanation for it. Okay, so we're trying to explain those numbers and then translate those into the real world. What do those numbers mean? Okay. Well, that's pretty much the opposite side of the bay. Now what we're looking at is the end results. Biology. Okay, you can see how expansive my understanding is of the real world. Biology, that's the only thing that's real, right? And other stuff. What other stuff could we say is in the real world? I'm sure we've got some of you in here. It's a hint. Begins with an E. Rhymes with bling. You'll see I'm very good at rhyming. See? Rhymes with bling. I was very good at rhyming. You guys didn't take me seriously, did you? So we're looking at engineering. How do we apply those mathematics into building things? Okay? Or constructing canals, or organizing where people live. Okay? A lot of that is the mathematics and physics. Okay? But how does the mathematics and physics actually make it over into the real world? And that's where chemistry really comes into play. A chemist comes through and explains, this material will work for you, Mr. Engineer, because the physicist says that these theoretical specs should work. So the chemist goes out, looks at the theoretical results, looks at the actual result that we want, and says, how can we make this material do exactly that? Okay? So our chemists really kind of bridge the gap between these two fields. Not that I'm biased or anything, but that's my opinion. Okay? When we go through and look at the fields of chemistry, everyone likes to call this class that you're in, or 151 and 152, inorganic chemistry. I usually find that to be pseudo a load of crap. Okay? What you're in is in general chemistry. General chemistry summarizes all fields of chemistry. We take a look at the entire periodic table, and we glaze over different aspects of it. What different pieces are in it? What different things control it? Okay? What can we do on a very simple, basic level with those pieces? Okay? Organic, biochemistry, inorganic, and physical now look at each of those individual sections, ultimately of the periodic table, and says this is what we can specifically do here. So when it gets into organic chemistry, organic chemists take roughly the first 10 elements on the periodic table. If we want to get really pushy, we might jump up to 18. Okay? And we'd say, I'm going to use those to build carbon-based things. Okay? They don't have to be living things. They just have to be carbon-based things. Okay? A biochemist comes along with a very similar perspective because biochemistry is looking at biology, which is based on organic material. So again, carbons. Except biochemists say that the efficiency of an organic chemist going in and physically moving individual atoms and making solutions is way too difficult. So a biochemist goes through and says, I'm going to enlist that bacteria to do it for me. Right? Which is why biochemistry is both interesting and, in my opinion, boring. Because you don't do anything in biochemistry, you tell something else to do it for you. Okay? So it's neat that we have that control over it. You move to inorganic chemistry. That's largely dealing with that center section, the lower, 21 to 30, are transition elements. Okay? Those are looking at those individual metals and how those metals can do different or have different properties that we might want to take advantage of. Okay? One of the biggest developments out of inorganic chemistry would be computers. Okay? Pretty much everything that we deal with in life today, all of our advances come from some form of inorganic chemistry. Okay? Then we've got the ultimate mathematical aspect of it. You can go all the way into physics, physical chemistry. I don't know why they get a separate branch, but I guess they're tied down enough in the real world that they get called physical chemists as opposed to just physicists. Okay? So those are kind of the approaches that we've got behind science and what Chapter 1 is really kind of driving at. Trying to get you sort of excited about it. Okay, so let's see. By show of hands, did I get you sort of excited about science? Stoked, even better. Okay. So now let's make it depressing and get into the real stuff. Okay. So what we'll do now is kind of shift. Instead of getting into the mathematics and the formulations behind chemistry, let's still keep it as that broader picture. Okay? So what we're going to do is look at matter. Right? Because that's really what chemistry is about. It's the interaction between any two things. So we need to know what those things are, and that's where we're looking at matter. So we're going to come up with different classifications for it. Okay? And when we look at chemistry, or any science for that matter, we can evaluate according to two principles, either the qualitative or the quantitative. Okay? If you're an organic chemist, you typically tend to think in the qualitative fashion. Okay? A little bit in the quantitative, but not too much. As far as general chemistry goes, I'd say most of it is quantitative, okay, which is a bit unfortunate, because how many of you have liked math? It was a pseudo-expected response. Okay? So most people have problems with mathematics, and so they come into a chemistry class going, oh my God, chemistry stinks, and now I have to do mathematics at the same time. Okay? So most people have a bad response to chemistry as well. Okay? But realize there is something beyond quantitative. We can also qualitatively analyze chemistry. What is qualitative if quantitative is numerical? What's the easiest answer, you think? Quality. I like that explanation, but not quite. Okay? Qualitative, we're looking at observables. We aren't adding a number to it. We're saying this change occurred. When I mixed these things together, they blew up. I mixed these two things together, they did nothing. It's a qualitative observation. So it's primarily just looking at a simple observation, but without really adding any numerical value to it. Right? And that's where a lot of chemistry started. Right? When we're trying to look at different forms of life. How can we make life? How can we try and get lead to turn into gold? They weren't concerned so much about the quantitative observation or the quantitative numerical numbers. They just wanted it to occur first. They wanted that observable. Okay? We go back to science, try and evaluate different things. A lot of it comes back to just a simple observation. Once you have the observation, you can then start to build a hypothesis and an experiment that you can then evaluate the quantitative results and bring numbers and all sorts of other math stuff into it. Okay? So, let's take a look at some qualitative observations about the world that we live in. So if we think back those, what did I say, it was 800 years ago. We're going to try and figure out what people might have observed. Yeah.
The earth is flat.
Okay, we could have seen something about the earth is flat. That's a very large observation, though. We're trying to get down into individual interactions between things. Okay, so while the earth is flat, is there something that we found was necessary for life?
Water.
Okay, water was really where I was driving for on that. I definitely heard something about oxygen. What's the problem with oxygen? Can't see it. So it's not an easy observable. We can build experiments where we know oxygen is present, but it's not the easiest thing to see. Water, on the other hand, is something that we could physically see, touch, and manipulate. Okay? So we could use water as our nice qualitative observation and try and see what conclusions we could come to about water. Okay? So what do we have here? What's happening in the upper left? What's that picture show? Snow. What can you tell me about snow?
It's a solid form of water.
Or ice. It is a solid. I can't spell solid. Let's try that again. There we go. Solid. Okay. What happens in that next picture? Okay. We have liquid water. Y'all are going to make fun of me for using capitals and lowercase. Let me fix that. I know, because I made fun of my professors for doing that too. Okay? And in that last case, I know that one's a little bit harder to tell. We're looking at pushing our liquid water into a gas. So we've got 3 ways to classify these. So if we think way back when, we could now go through and say, well, there's 3 components. We have solids, liquids, and gases. And that's what makes up all matter. And solids are different from gases, and gases are different from liquids. I left the liquids out. Okay, and they're all separate. Okay, well, is that the case? Is solid water different from liquid water? Is it a different compound? It's the exact same compound. Okay, it's the exact same species. But there's something else different about it. Okay? I don't quite want to get all the way into the structure there. The individual molecule will stick with being the same.
Doesn't snow 90% air, 10% water?
Okay, so we could look at actual compositions, but we want to take it even further back. Remember, you guys are adding in numbers and making it more difficult. Okay, I know nobody wants to make it this easy. Let's say we're way back when and we see this solid ice. Okay? It can take on a particular shape. We can compact it, and it holds that shape. Okay? And if we smash it up real tight, we can throw it at somebody and we can make it hurt. Okay? So we've got characteristics for this solid. If we then separate away from the solid and look at the liquid, we say, oh, well, we need this liquid to survive. Okay? We have to have, this is the life essence. Okay? We have to have this present. Okay? Our initial observation said these 2 things were different. Because if I try and ball up a little bit of liquid water and throw it at somebody, all the only thing that happens is I get wet. Okay? So that doesn't quite work out. So we say, yeah, they're different things. But are they different? What happens after it snows and the sun comes out? Okay, it melts. It changes phase and it becomes liquid. So a species, or two things that we said were completely independent and different things, end up becoming one and the same. Okay? So what we're trying to do is evaluate and say, these things, there's not just solids, liquids, and gases, but we can transition between each of these things and still maintain the same essence or the same species. Okay? And we know that it's the same because if we left that solid in a beaker or a bowl and then we drank it, that was still something that kept us alive. So we know that these things end up being the same. And then if we heated it up, what happens when we heat it up? It all turns up into the gas stage even further, and then it all of a sudden disappears. But let's say we got real creative and put some cold thing over the top of that. What happens on that cold plate?
Condensation.
You see some liquid water start to appear again. Okay, well, that means as I'm transitioning here, I'm still taking the same species and transitioning it through different phases or different states. Okay? Those phases are things that will make up matter, and what we're trying to do is figure out different compositions of that. What can we do with those individual phases of matter? Okay? How do we transition between each of these? Okay? If I go from a solid to a liquid, how do I do that? Okay, I add heat, so we can do plus heat. Here's a fun one. How do we do the reverse? Okay. I had a couple people this morning say throw cold at it. Well, okay, cold is kind of a weird thing to describe. In fact, heat and temperature in general is a weird thing to describe. Really what we're looking at when we look at hot versus cold is a source of energy and a lack thereof. So if I want to go from the liquid to the solid, what I want to do is look at the removal of that heat. Okay? What happens if we go the other direction, if we continue on? We go up to the liquid versus the gas. What do we need to do? Add heat and subtract heat. Same thing as we did before. Okay? If we now move to a different species, okay, say, I don't know, sodium chloride. Nice and simple. So NaCl or salt. Would I expect the same amount of heat to be transferred or necessary to be transferred to switch from solid to liquid and liquid to gas? Okay, according to our initial hypothesis, we can take any solid and switch it to a liquid by adding heat. Okay? We haven't quantified anything yet. So what we might do is say, we're still looking at different phases of matter, a solid and a liquid. Yeah, sure, why not? We're still just transitioning between those two. Let's say it takes the same amount of heat. So we go back to our observable. Is that the truth? Okay. When you heat up, in the easiest example, let's take salt and add it to liquid water. What happens? What happens to the salt? Solid salt. It dissolves. We no longer see it. It mixes away. If we then go through and heat it, say we're going to make a pot of pasta or something like that, put it on the stove, turn on the heat, and then walk away and forget about it for an hour. What happens? All the water boils off, and what's left in your pot? All the salt. Okay? We still added the same amount of heat. Why did the salt not go off with it? It requires a different amount of heat. Okay? So if we want to start referring to each of these transitions, we want to come up with something other than saying adding heat to go from solid to liquid or subtracting heat to go from liquid to solid. We want a more simplified way to reference those. Okay, so it's kind of a roundabout way of getting towards what do we refer to, what happens when we go from a solid to a liquid. Okay, there's a change in energy. Let's say a block of ice. Put it on the table in here, what happens to it? Okay, it melts, so it went from a solid to a liquid. And when you said what happened to it? It melts. So what do you think the point is at which we transition from a solid to a liquid? The point at which we melt, or the melting point. How about if we went the other direction? liquid to solid. Liquid to solid,
Freezing.
we're looking at the freezing point. Because it's freaking cold, right? Or it's freezing cold. Haha. What happens if we go over to the liquid to gas transition? What's that one? Now that you guys got the idea here. We've got a boiling point. And the reverse, gas to liquid. That one's a little bit trickier. We don't see that one quite as often. No, not a bad guess. It's condensation. So we're looking at a condensation. I don't think there's a point, but let's just call it a condensation point for the sake of it. Okay? Can we transition from the solid to the gas? Do I have to go through the liquid? Take a look at water. When was the last time you saw solid ice go into a gas? Anybody seen that?
Dry ice.
Interesting point. Is dry ice the same as ice? No, it's something else. What's going on with dry ice, though? Dry ice starts as what phase? Solid. Does it go through a liquid? No. So if we base our assumptions first based on just solely water, we say we can only go solid to liquid to gas. But there are other species that can jump between solid and gas. Okay? So we would again have to adjust our theory and say, yes, we can do that transition. What is that transition referred to, going from solid to gas? It's a harder one. Or gas to solid. Does someone know either of those? I think someone this morning cheated because I think they work at Intel and they actually work with these processes. Vaporization is another way of going from liquid to gas. That's still liquid to gas. Sublimation. Don't laugh at me. That's right, isn't it? Okay. How about the other one? Gas to solid. This one I actually didn't know, so I was really hoping someone this morning had it, and they did, so it was good. Deposition. Okay. So now we've got an idea on how we can transition between each of these phases. Why does CO2 go from the solid to the gas, but water does not? Because so far our theory only says heat. Okay. And if it's just heat that controls it, dry ice should not be dry. It needs to go through that liquid. So our theory is missing something. Okay? So we'd have to go back and reevaluate our experiments. So let's pick another experiment. In this case, I'm going to look at the boiling point, because that's usually the easiest one for people to see. It's also the easiest one for me to explain, so I'm going to cheat both ways. Okay? Let's boil a pot of water here. What happens when we take that same pot of water, we boil it in Denver? Okay. Does the altitude cause something to change with our boiling point?
Yes.
Yeah, it absolutely does change. Okay? I described it a little bit better this morning. We could look at cooking. Do cooking times change as we move from sea level to higher altitudes?
Yes.
Yeah. What's happening, or why does it take a different amount of time? What are we trying to do whenever we cook something? In most cases, the goal of cooking is to very controlledly remove water. Controlledly, I decided was a word, by the way. I saw a few puzzling looks. Okay? So we are trying to control the removal of water from our species, and in the process, other chemical changes can occur to allow us to get the final product we want. Okay? So when we change our altitudes, for some reason, the removal of water changes. So what else changes as we move altitudes? So the oxygen level changes indirectly. Why does the oxygen level change? The air is thinner. Okay, which is really the point we want to get at. It's not so much just that the oxygen is less, so is the nitrogen. So is all the other toxic, other nasty gases that are floating around. Okay? In general, as we move to a higher altitude, we reduce the amount of atoms in the air. What does that mean as far as another physical observable? Hazmat attack. Pressure. What happens to the pressure as we change altitude? It decreases. Okay, well, what is that pressure doing? Let's say we took some of that ice and we kind of held it there. Okay, just sitting on its own, it doesn't do much. But what happens if we put pressure on that ice? We can ball it up and force it to get tighter and tighter. Remember you said snow, you said was 90% air? If we take snow, we can compact that into ice. Okay? So by putting pressure on it, we can kind of change the alignment. Okay? What's happening is we go from a solid to a gas. That solid will sit on its own. I took that solid in my hand, it's going to sit right there. What happens when I turn it into a gas? Is that water vapor going to stay right in the center of my hand? No, where's it going to go? Everywhere within the room. It will entirely fill the volume that we're in. Okay? So what we're looking at is pressure also affecting that. In the case of a gas, the pressure on the outside isn't pushing it hard enough, and our ice particle starts to shatter outwards. There's nothing holding it there. Okay? So we get both an external force of pressure holding things in and an internal force. That internal force is controlled by our heat. If we add enough heat, we can start to break the internal forces holding things together. Okay? So when we're looking at these transitions, it's not just heat. Well, I kind of ran out of space. So with heat and pressure, they're going to control some of these transitions. Okay? And so a lot of the things that we're going to evaluate this semester, or some of the things, are going to be heat and pressure. How do we measure those? How do we monitor them? What things do they control or not control? Okay? Any questions about those? Yes?
So how would you make ice into dry ice, and then how would you make steam or like gas
So,
into snow?
by ice into dry ice, do you mean water in its solid going from its solid to its gas state? Okay, just wanted to make sure, because dry ice is CO2, it's not water.
Oh, okay, that was just the example.
Yeah. So when we look at water, can we force it to go into the gas directly from the solid? Yeah, we can. What do we have to do? We have to adjust both the heat and the pressure. And if we control those to the proper amounts, we can cause the solid made up of water to transition directly to the gas state. Okay? An easier experiment, though, because that requires also a real drop in pressure. An easier experiment would be to take CO2, and you can see CO2 actually form liquid CO2. It's a little bit dangerous, so you might need to trust the container you're using. But if you put CO2 in a closed container and close that down real tight, it needs to be strong enough that it doesn't explode. Okay? Just prefacing with that. You can actually build up enough pressure from the solid CO2 turning into a gas that it now puts so much pressure on the gas that it converts into a liquid. And you can actually watch CO2 go from a solid to a liquid to a gas. You can see all three states in the same container. Okay? It's kind of neat. And as soon as you release the pressure, the whole thing turns into a solid. It's kind of cool.
Isn't it this kind of the same process that was used to put to make nitrate into ammonium?
Nitrate into ammonium is looking at a different process. You definitely have a different chemical formula. So you have to do a different, you actually have to force the reaction to occur. In that case, I think you are using strong pressures of hydrogen gas. I'm not sure on the exact transition for that, but that's a different process. Okay? Other questions? Okay. Remember this part, because when we come back to it, probably in 10 weeks, I'm going to say, you remember when I talked about dry ice being 3 phases? Okay. So let's make some qualitative observations. If we take a look at the shape, so I tried to organize these via columns. Take a look at the shape for a solid. Okay. Textbook says one way to describe it. I'm not quite sure I believe it. Okay. Say that the shape doesn't change. If I take a square block of metal, can I turn it into a round block of metal? Sure. Yeah, so when they're talking about shape, they're saying if you just let it sit on its own, it's not going to change its shape. So our shape is fairly immutable. When we move to liquid water, what's the shape? Whatever container it's in to a certain extent. So it will tend to fill the space equal to its volume. Okay? When we go through and look at the volumes between solids and liquids, okay, those volumes are going to be largely dependent on the material itself, okay, so the solid or the liquid. It's not dependent on the container that holds it. Okay. If we look at compressibility, what's compressibility looking at? How much can we compress that down? If I take solid ice and push on it, okay, a block of ice, can I really change its volume all that much? No. If I can't really change that volume, we're looking at its compressibility not changing as well. Take a look at liquid water, same idea. Okay. Can we compress liquid water so that it takes up a smaller volume? We can change the shape of that volume, but it's still going to be relatively the same volume. So our compressibility for both solids and liquids is relatively minuscule. We can't really adjust those. When we move into the gas, what happens with the shape? Okay, it can take any shape, the shape of whatever container it's in. It's going to fill everything. If we go to the volume, same thing. If we take a gas, say even a single particle, okay, and we put it in a 5 ml container, we could then say the volume of that gas is 5 mils. If we put that same particle in a 20 ml container, right, the volume of that gas is now 20 mils. So a gas will fill whatever volume it's in. Okay? Compressibility. Could we compress a gas? If I took one particle and put it in a 5 ml container and moved it up to a 20, what's to say I can't do the reverse? Yeah. We can compress gases a lot. And that's one of the reasons why we take advantage of them a lot with hydraulic systems as well. Okay, we can look at those pressure changes. It's actually our combustion engine runs under the same principle. Okay? It's that compressibility that allows us to actually produce some pretty cool utensil or uses for everyday life. So now we can shift into matter, looking at a broader topic on what makes up matter. So we've got the phases that make up matter, and then we want to look at how we can interact those different phases with each other, okay, or not interact them at all. So matter really can break down into two separate categories. We can end up with mixtures and pure substances. Okay? Those then further break down into two more subcategories. So let's evaluate the mixtures. We get heterogeneous and homogeneous mixtures. What does a heterogeneous mixture mean? Different.
They don't blend.
Okay. Not blending or bending, as my spelling may show. What about a homogeneous? Okay, ultimately the same. Even go with even. Okay, so let's pick some examples here. Let's say we take salt, okay, solid salt. We all know what solid salt does, right? And let's add it to water. What happens when we add those two? What happens to the solid salt? Dissolves and disperses throughout the water. Which kind of a mixture do we have here? Okay. So that solid salt is now completely and evenly dispersed within the water. Oops, I gave a hint away there. We're looking at a homogeneous mixture. Okay, it's completely mixed in with it. So if we take a look at our saltwater solution, that's going to be our homogeneous. Well, what about a heterogeneous mixture? Okay. I'm going to come back to oil and water. let's take another solid. Let's take sand and water. So sand is a nice good solid. Let's add that to our water solution. What happens? Shake it up. What happens? Okay. Solid settles out, and we have a heterogeneous mixture. They are mixed into the same container, but it's now heterogeneous. What's heterogeneous about it? Yeah, I was hoping for some more key words that we just talked about.
Water doesn't dissolve the sand, or the sand doesn't dissolve into water.
Yeah. Liquids and solids refer to phases. So when we're looking at a heterogeneous mixture, we're looking at different phases. Okay? Those different phases are clearly distinct. We can see the different phases. Okay? So this is why I want to do the oil and water as a separate example. Let's take oil and water. What phase is oil? Liquid. What phase is water? Liquid. So when we take those two and we mix them together, we have two liquids, which means that's the same phase. What does that suggest? Homogeneous, except, did I write it under homogeneous? No. Why not? Those two phases don't mix with each other. Okay? Or it's bad to say don't mix. They don't evenly disperse within each other. They separate out, and we see a clear separation between the oil phase and the water phase, even though they're both liquids. Okay? Kind of makes sense? What happens when we shift over to pure substances? Okay? Pure substances can break down, actually before we get to pure substances, how can we take our mixtures and convert them into pure substances? Take salt water. How can I separate the salt from the water? We could boil it. That's a good way to do it. We could boil the water, collect the water as a form of distillation, and we've got the salt left over. Okay? To do that, what we did is physically change the states. So what we're doing to convert between a mixture and a pure substance is to do a physical change. Okay? What about sand and water? Okay, we could just filter it, put it through our coffee. Well, you probably don't want to do it through a coffee maker, but the coffee filter would work. Okay? The sand stays trapped on the filter, the water runs through. What if we had sand and salt?
Filter it, then boil it?
Sand and salt, there's nothing to filter. They're both solids.
Oh, I thought you meant
Put it in water.
You could put it in water, then filter and boil. There's another way you could do it, but that's the best way to do it, in my opinion. Can you see a difference between sand and salt? What if you put it under a microscope? Yeah, you can see it. So how could you do it? You could physically separate each grain of sand away from each grain of salt. Believe it or not, there were very important scientific discoveries done by doing exactly that. Individually separating individual crystals away from each other. Okay, they did some pretty cool, though tedious stuff. So we're looking at, again, a physical change. Okay? So those physical changes typically involve changing the phase, doing our separation, and then coming back to our pure substance. Our pure substances can then break down into two other categories. We can end up with compounds and elements. What are compounds? What are elements? Okay, or maybe an easier question would be, let's just stick with elements. What are elements? And since none of you all are following me around the room.
A substance that cannot be broken down further by a chemical reaction.
Oh, that's cheating too. What's an example of an element? There's a reason I'm holding my arms out. I am attempting to point. What do we have on our walls? Periodic tables of elements. Each of those species on each of these tables is an element. These are all of the elements in our known universe. Okay? If we put these different elements with each other, and in the process they form very strong interactions, they form bonds, we now have a compound. Okay? So the compound is a mixture of elements that have chemically changed the characteristics of those individual elements. So the relationship between these two is I'm definitely not going to have enough space to write that. Try it sideways. We're looking at a chemical change to transition between those compounds and elements. Elements, at least initially, were thought to be the smallest particle. Okay? They were the flour, they were the salt, okay, in our pie. We then could combine those together to build a larger structure, our pie or our compounds. So these are made up of our elements. As long as we have that permanent bond or physical bond between those two elements, we now have that compound. If we take multiple of those compounds and we put them near each other, now we have a whole bunch of that type of compound. Okay? Are elements the smallest particle? No. Okay, let's see how far down we can go. What particles make up elements? Everyone said that last time too. So what is the difference between an element and an atom? What's the difference that you guys are definitely putting into it, which is new to me? Bringing in a number. Okay, you're saying an element has to be more than one, and an atom is one. The definition of an element says nothing about the number of them. It just says it is an element. I can take a single, let's pick a good one. Let's take a single gold atom. That is an element. The element is gold. I happen to have one of them, so it is an atom. What is the symbol for gold? AU. Okay? So what is smaller than an atom? Might be a stretch, we're just curious. What's that?
What it's made out of, protons, neutrons.
We could go down to what makes up an individual atom. Protons, neutrons, electrons. Okay? We found those within the last 100 years. Protons, neutrons, and electrons were really first identified and manipulated right around the turn of the, let's just say 1900s, that way I don't get it wrong. Okay? Are those the smallest particles? Are you keeping up with sciences? We get the Higgs boson. There's even smaller particles than protons, neutrons, and electrons. Okay? Do we have to deal with the smaller particle or the really small particles? No. What we're going to deal with are protons, neutrons, and electrons. We aren't going to deal with anything smaller than that because that's above my pay grade. So let's just call it at that because I definitely wouldn't be able to explain it to you well enough. Okay. Though, how many of you know anything about those particles? Oh, okay. Well, a few of you do. I was going to say I could just make it up and then it wouldn't matter. But so unfortunately, I can't even make things up now. Okay. So what we can now do is evaluate what's going on with these elements. Okay. So this is why we have a periodic table of elements that summarizes all of the individual components that we can use to build larger compounds, also known as molecules. Okay? So if we've got this periodic table, what we're going to try and do is evaluate different ways that we can categorize it and understand different aspects of it. Okay? So the first thing that we talked about already today was solids, liquids, and gases. Okay? Does our periodic table give us any information about solids, liquids, and gases?
Organized.
We can get a yes and a no on this one, so both answers are fair. Who says yes? Or actually, let's stick with who says no. Nobody says no, seriously? If you look at those projectors, look at the projector screens, where does it say solid, liquid, or gas?
They're separated into different categories.
They are separated into different categories, but is one category a solid, liquid, or gas? Not on the periodic tables on our projectors. Okay? No point do we have those separated based on solids, liquids, or gases. They are separated based on other things, and there's a lot of rhyme and reason behind how we build the periodic table. But this periodic table says nothing about what's a solid, what's a liquid, and what's a gas. Okay? So there was the no answer. Where's the yes answer? Are these the only two periodic tables in the room? We got some up on the wall. take a look at the ones on the wall. Do you notice any big differences that kind of stand out? Some of those are colored. What do those colors mean? Okay. Anybody know any element on that periodic table? Feel free to shout one out. Oh my gosh. Okay, maybe that was a bad policy. I think I heard nitrogen. Let's stick with nitrogen. So whoever said nitrogen, what phase is nitrogen found in?
Yes.
Gas. What color is it on the periodic table up there?
Red.
Red. Okay, so now let's focus on the red elements. Okay, of those red elements, do you know any others? Oxygen is O.
Helium.
Okay, helium.
Argon.
What can you tell me about the phase of oxygen, helium, argon, any of those? Gases. What do you think the red means? They're all gases. Okay? They aren't all noble. Okay. Any other element that you know? Don't tell me nitrogen, oxygen, fluorine, chlorine, helium, neon, argon, krypton, xenon, or radon.
Bromide.
Or bromine. I can stick with bromine. Okay, what's the difference with bromine? I know it's a little bit difficult to tell with bromine.
It has a color.
Okay, it has a color. What's its color?
Yellow-green.
On the periodic table.
Oh, blue.
It's currently blue. How many other elements are blue? There's one other one, mercury. So Hg is mercury and bromine is Br. Okay, what phase? Do you guys know anything about those in their natural phase? You sure? Yeah, you're right. Mercury and bromine are both liquids. They are the only elements that are liquids in their elemental states, so at room temperature. Okay? Mercury is kind of a fun one. Where have you seen mercury potentially? In thermometers. They're typically showing up in thermometers because they have very natural responses to temperature, okay? Controlled volume changes. We could then use that to determine temperatures or a way to measure the temperature of a system. Okay? You typically don't see that anymore because mercury is extremely toxic. It's very unpleasant to have mercury poisoning. I have a friend that's got it. Not particularly pleasant. Okay? And it's not easy to fix either. Which also brings up some other interesting points. Feel free to go ahead and check out online. One of the other interesting properties for mercury is that it is extremely dense. Okay? What does density have to do with anything? If I walk on something that is very dense, what tends to happen? Float. So we can take liquid mercury, and there's pictures of this, vats of mercury where they pulled it out of the ground, okay, and then processed it and turned it into pure mercury, where they'd have miners just sitting on top of it, lying there, and you see the liquid shifting around them. Okay, that's kind of neat. What do you think black means on the periodic table now? The only phase left is our solids. Where else could we pull that from? Well, do you know any of those black elements? Lithium, right? You know of lithium solid? You've seen that one? Okay, it is definitely in a battery. I just would have expected other elements that were more stable, but that's fine. So we've got iron with Fe. Okay, other elements up there? Aluminum, Al. Okay. We're looking at solids for all of the elements that are in black. Okay, so we've got a lot of information stored in these two periodic tables that are up on the wall.
What about the white?
It's a good question. And at this point, I'm just going to guess. Pretty sure those are unstable.
I also believe they're like man-made as well.
Synthetically prepared. There we go. So that works. So they are all synthetically prepared, meaning someone in the lab smashed them together to make those elements. They're not things that we can find naturally in our environment, okay, in any compound or mixture. So that's kind of neat. We can make a whole lot of elements. It's kind of fun. Okay. Other things, because I got a little bit of 5 minutes. We can look at metals, nonmetals, and metalloids. Okay. So that's an extra piece of information that we can put together on our periodic table. Okay. Anybody know which of the any metal on the periodic table? Any metal? Iron. Iron, like it. Iron's a metal. Any other metals?
Tin.
Tin. Where's tin? Good. Tin is SN. Where else do we have metal? Nickel. Aluminum. Come on, we still got like 60 of these. Keep naming them.
Yeah, aren't most of those metals? I mean, that's what I read.
Yep.
I thought that was interesting.
I was actually kind of being mean. I don't want you to list them all off.
Yeah.
Most of the periodic table is a metal.
I found that interesting.
Okay? Or classified as a metal. If you take a look at the ones on the board, those periodic tables don't have a very clear delineation. I did that intentionally because I didn't want you to give too much of the information away. If we take a look at the periodic tables on the walls, do we have a delineation between the halves? If you look really carefully at boron, there goes what? Shoot. I did that line wrong. No, I didn't. According to that, I did it right. Okay. We get kind of a sharp line that goes through there. Okay, or at least that's what our periodic table is showing. Okay. What is that separation going to be?
Those are the semi-metallic.
We've got our metals, and that's sure legible, right? You can see all that. So all this stuff, we're looking at metals. What's happening on the other side? We got non-metals. What happens when we transition between metals and non-metals? We're in some weird gray area. Who knows what that weird gray area is? We can call it semi-metals. We can call it metalloids. So your your textbook colors those slightly differently. I think that's what I started to have memorized. Your metalloids float through the middle. I'm just going to color them over the top. Silicon, germanium, yeah. Those are your metalloids. So they don't carry the properties of nonmetals. They don't carry the properties of metals. They kind of overlap. They're in that gray area right between. Notice where they sit, right on that boundary between our metals and nonmetals. Okay? So I'm going to be really nice to you guys and let you out early. 2 minutes. I will get this posted. I have decided that your lecture is definitely better than the morning.